Our next goal is to classify all absolute values on a number field. In particular, we're going to talk about Ostrosky's theorem, which says that every absolute value on the rationals is either equivalent to a p-adic absolute value or to the usual absolute value on Q. That's going to be the topic of the next video. For this video, we have to first define what it means for two absolute values to be equivalent. Recall that the reason we're interested in absolute values is because we want to bring tools from topology, geometry, and analysis into the study of number fields. This can be achieved by means of having a metric on the number field. Now, every absolute value naturally induces a metric. The distance between x and y should be defined as the absolute value of x minus y. With a metric, we can then define the notion of open balls, and thus we get an induced topology with fundamental neighborhoods being these open balls. It makes sense then to define two absolute values on a number field K to be equivalent if and only if they define the same topology on K. So now let's say that we start with an absolute value on K. We can then ask, what are all of the absolute values equivalent to this one? Well, there is an easy example of an equivalent absolute value, namely any absolute value that is a power of our original absolute value. This is because if this green absolute value is a power of this yellow absolute value, then for every point x in K, x lies in some green ball if and only if it lies inside some yellow ball with the same center. That means every green ball is contained inside some yellow ball, and vice versa, and thus the two topology must be equivalent. Therefore, we see that if two absolute values are positive powers of one another, then they define the same topology. Of course, now we can't resist but ask, is the converse true? Is it true that if two absolute values define the same topology, then they must be powers of one another? The good news is, this turns out to be true. So let us prove this now. We'll do so by first showing that if these two absolute values define the same topology, then their unit balls at the origin must contain each other. After that, we'll show that this must imply that one of the absolute value must be a power of the other one. So let us first show this implication. This is actually quite simple because x lies inside this unit ball center at the origin if and only if the sequence x to the n converges to 0. But since these two absolute values define the same topology, x to the n converges to 0 in the yellow topology if and only if it converges to 0 in the green topology. And that happens if and only if x lies inside the green unit ball center at the origin. Thus we see that these two absolute values define the same topology. All elements with yellow absolute value less than 1 must have green absolute value less than 1, and vice versa. Now, let us use this to show that one of these absolute values must be a power of the other one. Alright, so let us suppose that these two absolute values define the same topology. Now we need to show that green is equal to yellow to some power alpha. Now how do we find this alpha? Well, that's a piece of cake because we already know that this is gonna hold, right, for every element in K. So we might as well just use a test element. We can take some appropriate element x0 in K and assume that these absolute values are not trivial. Then these are just two real numbers, so I can find some exponent here, right, such that this is equal to this number to the alpha. Alright, so now by definition, we see that this equality holds for x0. We need to show that it holds for all x in K. To that end, given an arbitrary x in K, the first thing we should do is to relate x to x0. And again, since both of these are positive real number, we can find some positive number beta such that this is a power of this to the beta. Now we can relate this to the yellow absolute value of x0 using this identity here, using the definition of alpha. From here, we see that then it suffices to show that the yellow absolute value of x is also a beta power of the yellow absolute value of x naught, right? Because if we can establish this, then we see that this green absolute value of x is just gonna be the yellow absolute value of x to the alpha. Alright, so now let us show this. Alright, so this is what we have. So for the green absolute value, we have this relation between the absolute value of x and the absolute value of x naught. Now we want to deduce the same relation, but for the yellow absolute value. And this is where we're gonna use this lemma here. This property allows us to relate these two absolute values. Alright, so first step is to divide both sides here to bring everything to the case of absolute value 1. Now, this condition does not yet look like this, so we need to massage it a little bit. Without loss of generality, we can assume that the green absolute value of x naught is greater than 1. Otherwise, we can just take 1 over x naught. You might ask, well, what if the absolute value of x naught is 1? Don't worry, since we assume that these absolute values are not trivial, i.e. they are not constantly 1, there must be some x naught with absolute value not being equal to 1, and thus either x naught or 1 over x naught must have absolute value greater than 1. In that case, if we increase this exponent a little bit, then we have that this must be less than 1. Now, by the property that we have established here, we know that this absolute value here must also be less than 1. Now, if we take a sequence epsilon n that goes to 0, then taking limits of both sides here, we get that the yellow absolute value of this quotient must be less than or equal to 1. However, observe that we can repeat the same argument, but here we're reducing the denominator. This would imply that the yellow absolute value of this is greater than 1, and so again, taking limit gives us that this quotient is greater than or equal to 1. Therefore, it must be 1, and the yellow absolute value of x must be equal to the yellow absolute value of x naught to the p beta. Now, since by definition of alpha, we know that this absolute value here is just gonna be equal to the yellow absolute value of x naught to the alpha beta. Therefore, comparing these values shows us that this green absolute value must be equal to the yellow absolute value to the alpha. Thus, we have established that two absolute values are equivalent if and only if they are powers of each other. In the next video, we're gonna classify all absolute values on the rationals.